Hello and welcome to the latest webinar on Fibre Channel, sponsored by the Fibre Channel Industry Association. In this presentation, we're going to be diving headfirst into the depths of Fibre Channel NVMe. And today, our agenda is extremely full. But before we get into it, allow me to give you a couple of insights into the platform that you're using. If you've never used the BrightTalk system before, you'll notice that there are a few buttons next to the presentation window. The first button is to notice the question button. At any time during the presentation, you can ask us the question, and I will do my best to make sure that it gets asked. If we run out of time, or if we have to defer to the question until later, we will be collating all the questions for a Q&A blog that we'll be posting at fibrechannel.org. And the other button I'd like to draw your attention to is the ratings button. We take your feedback very, very seriously, and we encourage you to leave comments and rate the presentation at the conclusion. So if there's any subjects, for example, that you'd like us to cover in the future, you can feel free to make those suggestions in either the question area or in the comments at the end. And finally, I'll get this out of the way right now. These slides will be available for you after the conclusion of the presentation. There's always a few questions about whether or not they can get them, and yes, you'll be able to get them. The link for where to find them will be shown at the end of the presentation. That's the cost for attendance. Now, regarding today's presentation, we're going to be spending a lot of time about the specifics of the new FC-NVMe protocol. But in order to do that, we'll start with some terms and definitions for Fibre Channel and NVMe. Once we do that, we're going to be able to zero in on the bits and bytes, quite literally, of FC-NVMe before finally discussing a few of the use cases that many people will find useful. Now, today's presenters, the people who are going to be educating you on this, are none other than two fantastic rock stars. First, we have Curt Beckman, principal architect and co-author of the FC-NVMe for Dummies booklet. And we have Craig Carlson, chair of the T11 FC-NVMe committee and also a member of the FCIA board of directors. And the two of these fine technical gentlemen are going to tell you everything that you wanted to know about FC-NVMe. Me, I am your cheerful MC and host, Jay Metz. I am going to be asking some of the questions on your behalf and helping the program move along. So, before we get really into it, I'm going to hand it off to Curt in a second. I want to give a little bit of a level set to make sure that you understand what this presentation is going to be about. Now, as I mentioned, we're going to be talking about advanced, deep look into how FC-NVMe works. And we're going to apply that to how some of this applies to use cases in the data center. However, because of the time limits that we have, we are not going to be able to do a tutorial on Fibre Channel or even NVMe over fabrics. FCIA has sponsored an excellent introduction to both Fibre Channel and FC-NVMe. And if you're finding yourself that you need a refresher, we do encourage you to consider those as prerequisites for the material that we're covering here. The webinar website is located on the page here. We're also not going to be discussing a comparison or a shootout between Fibre Channel and other NVMe over fabrics and transports. That falls outside the scope of this presentation. So, without further ado, we have a lot to go over. So I'm going to hand things over to Curt Beckman. Curt, it's all you.
Thank you, Jay. And now let's advance to the content slide here. What is Fibre Channel? In case you happen to be more of an NVMe type, we'll give you this, and then you'll have these reference slides available as well. Fibre Channel is a network that's built for storage. It's not a general purpose, all application kind of a network. And it describes a number of layers. It describes the physical connection between the host and the target, as well as the logical protocol. And it also defines a set of fabric-based services. So these services are actually delivered by the devices in the fabric to support the host discovery and connectivity and so on. Moving along, what are the design requirements? So the goal was to basically mimic a parallel kind of connection. So it offers a one-to-one connectivity, but also allows devices to connect, say, initiators or hosts to connect to multiple targets. All the services are in the same devices, as mentioned before. That's where the fabric-based services come into play. And there's well-defined initiator and target relationships in the network, which comes into play in a moment, effectively influencing the north-south traffic picture. And the fabric, the network, is designed to eliminate packet drop, so it is effectively a lossless transport. Now, network designs based on this are designed for maximum availability and data center scale. So the high availability comes through, in part, through a dual fabric architecture. So it's standard practice to have an A SAN, B SAN with an air gap, so no shared components, no shared cables or anything. And the most common topology is an edge core model versus some edge core edge kind of models that you sometimes hear about. But because Fibre Channel supports is a fabric architecture, not just a tree architecture, it's actually topology independent. It's topology agnostic, I would say. Although, as mentioned, edge core is the most common model with storage, which is a smaller percentage of the connections. Typically, there's more initiators and smaller number of targets. The targets are typically connected to the core. And this is how we deploy our services, the fabric-based services. Some basics in terminology. There are 3 defined classes for Fibre Channel traffic delivery, but Class 1 has been deprecated and is no longer in use. And Class 3, the unacknowledged datagram service, is the one that is most commonly used and is what is used by FC-NVMe. Each unit of transmission in Fibre Channel is called a frame. They can be up to 212 bytes, 2,112 bytes long, so essentially large enough to carry a 2K byte payload, including all the encapsulation and overhead. Multiple frames in a given direction can be linked together as a sequence, but there is a notion of a single frame sequence. So even if it's just one frame, we may still refer to it as a sequence. And then sequences can be connected together or linked together in an exchange that has a specific identifier. An exchange is all the frames in an exchange are guaranteed to be delivered in order, and part of that is that the fabric is free to send different exchanges along different paths, depending on for traffic balancing, load balancing across different links, but by ensuring that a single exchange always follows the same path, then it ensures in-order delivery. The Fibre Channel, the FCP, Fibre Channel Protocol, includes data transfer capabilities. FCP also defines upper layer stuff, which has traditionally been associated with SCSI over Fibre Channel. The data transfer portion of FCP is the same data transfer that has been adapted for FICON, that's FCSB, as well as what we're talking about today, FC-NVMe. So we're talking about exactly the same data transfer capabilities. And as we know, it's been created to provide very high speed and low latency transport. And now to cover a little bit of NVMe background. First, we'll take a step back and just make sure that we're providing the right context. So the earliest NVMe specification is focused on the PCI bus. It actually defines a software interface protocol on top of the PCI physical layer, and it's really defined for NVMe-based SSD modules to plug into the PCI or directly into a server PCI bus or into a PCI expander. So it's got very small scale, essentially server scale, or potentially sort of sub-rack scale. Those same modules have now been, a number of target vendors, storage target vendors, have enabled their arrays to accept NVMe SSDs plug into a PCI bus on the backside of their flash arrays. And I say flash, but next generation non-volatile memories such as Intel's and Micron's and other vendors' technologies would also apply in this case. So both of those are the same PCI-based modules. So the first phase plugging into servers, the second phase plugging into the back of storage arrays. And now what we're talking about is NVMe over fabrics, which is the abstractions of the NVMe protocol, the higher level notion of NVMe being overlaid on top of, well, there's a series of fabrics, but today we're talking about the Fibre Channel fabric. So in the second phase, when we had NVMe modules plugged into the back of the flash array, you could speak SCSI over Fibre Channel to talk to those NVMe devices on the back end, and the flash array took care of the mapping of the protocol. Now in this third phase, we're talking about running the NVMe protocol natively across Fibre Channel to the flash array, which then can pass it on down to its PCI connected NVMe devices. It may be in principle that some implementations will find a way to connect to legacy devices, but the NVMe over Fabrics picture is intended to connect the NVMe speaking servers across an NVMe speaking SAN and through the flash array to the NVMe modules. Some terminology. So we're talking about NVMe over Fabrics. The shorthand for that is NVMe-oF, spelled in, with a hyphen there, as seen there. It's the preferred abbreviation, the preferred acronym. NVMe talks about a host as the system which issues the commands. We would call that an initiator in Fibre Channel terms. The subsystem is the sort of target side terminology, although it's not entirely a one-to-one mapping between a subsystem and a Fibre Channel target, as Craig will explain in more detail. A capsule is a unit of information exchange over which NVMe information is sent across NVMe over Fabrics and contains commands and responses. There's a notion of a discovery controller that's a part of the subsystem that you can talk to learn more about specific NVMe-oF information. That's distinct from the discovery service that's part of the Fabric-based services in Fibre Channel. There's a number of queuing terms that are important in NVMe and are available both in the basic NVMe over PCI, but also in NVMe over Fabrics and in particular NVMe over Fibre Channel or FC-NVMe. There's a submission queue, which is where we submit our commands, and a completion queue, which is where the status and return data is sent back by the controller. There's an admin queue for administrative commands. There's also two kinds of queue entries, a submission queue entry for the submission queue and a completion queue entry for the completion queue. And with that, I will pass it over to Craig for the in-depth discussion of FC-NVMe, and I'll be talking to you later on.
All right, thanks, Curt. So what are we going to look at in this section? So basically, we're going to do a deep dive into how NVMe over Fabrics is mapped on the Fibre Channel. And we're also going to take a closer look at how discovery is done for FC-NVMe. So stepping back for a second to the goals. The goals when we designed FC-NVMe were such that, first of all, we wanted to make sure that we complied with the NVMe over Fabrics spec. And then, of course, we wanted to have high performance, low latency. And we wanted to be able to use existing HBA and switch hardware. We didn't want to have to spend new hardware, new ASICs to support FC-NVMe. We wanted the FC-NVMe protocol to fit into the existing Fibre Channel infrastructure. And we also wanted to maintain the connection to Fibre Channel services such as the name server, zoning management, and so forth. So for performance, of course, the goal is high performance, low latency. And we wanted to use existing hardware acceleration to achieve this goal. Historically, Fibre Channel does not have an RDMA protocol. So we turn to the protocol which is commonly deployed and hardware accelerated in most HBAs. And that's the FTP data transfer layer that is currently used for SCSI. It's been extended to FCSB, FICON, and now we're going to use it for FC-NVMe. So in order to do this mapping, we have to map the NVMe over Fabric capsules, which are the commands and responses, onto FTP information units, which is Each frame or packet in FCP is called information unit. And then we need to map these I/O operations into fiber channel exchanges. And so the mapping of the different information units looks like this. There's, first of all, to send an FCP command, FC-NVMe command, sorry. The initiator will send a SQE, which is the queue we call is the submission queue entry, which contains the NVMe command, to the FC-NVMe layer, and that will then encapsulate it into an FCP command IU, and it's really a FC-NVMe command IU, though it uses some of the same code points as the FCP command IU, but it's formatted for FC-NVMe. The data, any data that's sent, read or written, is then mapped into FCP data IUs, and data IUs for FCP, FC-NVMe or SCSI look the same. It's basically just a bunch of data. And of course, for those of you who are familiar with how the FCP protocol works, there are also maybe transfer readies coming back as well. And then for targets, on the target side, when the command completes, the completion queue entry, which is the NVMe response, is mapped into a FCP response IU. So diving into this a little bit more, the I/O operations then are also mapped into a exchange. If you recall, exchanges are the collection of sequences, for protocols like FCP, which applies to both SCSI, FICON, and FC-NVMe, an exchange map is a one-to-one correspondence to a command. So each command is in its own exchange. And so each exchange, the data, the frames within the exchange are guaranteed to be in order. Now, of course, the exchanges themselves can be reordered by the fabric if the fabric finds a more efficient path. So what does the command IU look like? If you're familiar with the SCSI, FCP, CDB command IU, you'll notice that the FC-NVMe command IU is pretty different. It's changed to be optimized for FC-NVMe, and the way we can do that is by looking at, if you look at the first two bytes in the command IU, those are unique identifiers. The FD28 are unique identifiers for FC-NVMe. No other FCP frame command IU will have those bytes. Those are values that have been assigned both by T10, which is the committee that defines SCSI, and T11, which is a committee that defines Fibre Channel, to be unique values for FC-NVMe. The next important field is the NVMe connection identifier, and this is a unique identifier which indicates an active connection between an NVMe host or initiator and a target or a subsystem controller. Then there's also a command sequence number, which allows the NVMe commands to be reordered if they're unordered by the fabric. There are only a few NVMe commands that require in order. Most commands don't require that. And then, of course, there's the NVMe SQE, which is the actual NVMe command itself. So for responses, there actually are two types of responses. There's a what we call fast path response, and this response is returned for only good response, only if it's a successful command. It allows for fast hardware processing, and it doesn't have any order requirements because there's really no information in that response. It just says everything's good. And then there's also the extended response, which contains a full NVMe response. This one potentially has slower processing time, and this one is required to be processed in order. So the fast response format is fairly simple. It's just a bunch of zeros. It just basically says all's good here. You can close out this command. It was successful. The extended response frame is a bit more complicated. It contains a response, a result field to indicate success or failure. It contains a response sequence number, which indicates the order which responses were sent, so they can be reordered if need be. And it contains a total data transfer length, which is the amount of data that was actually transferred if there was data transferred with the command being responded to. And of course, it also contains the full NVMe CQE or command or response. So how do these two interact? It's a fairly robust set of rules. I'll just summarize them here. Essentially, the extended response is required to be sent 1/10 of the time. So if you had a queue of 1,000, a depth of 1,000 entries, every 100 responses would be required to be sent, an extended response. And this is just to make sure that nothing gets out of sync in terms of queue pointers and buffer-to-buffer credit resources. An extended response is also required to be sent if the queue is starting to become full, or if the queue is becoming empty. And of course, if there's an error condition and the status needs to be sent, that also is a extended response. Now, of course, we also need to transfer data. That's the whole point of a storage protocol. And data in NVMe is presented as SGLs, which stands for Scatter Gather Lists. And some of you may be familiar with this. Scatter Gather List is basically a list of memory locations that the HBA can read and write. It's usually done via DMA or direct memory access to those locations. So for Fibre Channel, since we can't send the list of memory locations across the wire, we move the data presented in the list into a SCP data IU. And for writes, the local host gathers the data from the memory and sends it into the data IU. And for reads, the HBA presents presents a list of memory locations that the read data will be stored in when it's received.
So, Craig, this is actually a good time to ask a question, or ask a question that came in. And if you don't mind going back one slide, back to the response rules. I think not the response rules, the data transfer, excuse me. The question basically came in about what the difference is between NVMe over Fabrics and Fibre Channel NVMe. And your discussion about the the SGLs and how all NVMe over Fabrics uses SGLs, that seemed to be dovetail really question with what was asked. And so, what would you say the differences are between NVMe over Fabrics and FC-NVMe?
Well, there's a terminology difference there. There is no difference between NVMe over Fabrics and Fibre Channel NVMe because Fibre Channel NVMe is NVMe over Fabrics. If you're talking about NVMe over RDMA, that's where the difference takes place. And NVMe over RDMA uses the RDMA protocol. And RDMA protocol has ways of setting up direct read and write lists of pointers into remote memory, and that's really the key difference.
Right. Okay. Thanks a lot.
Okay, where was I? I was on. Okay. So a right example for the SGLs is, so on the left, the HBA is presented with an SGL by the NVMe layer, which points to a set of memory locations. And the FC-NVMe HBA then takes those memory locations and moves them into FCP data IU. and that's what's transmitted across the wire. And then on read, basically a set of locations, available memory locations, are sent to the HBA, and that's shown on the left. And then the command itself is sent with a really appropriately sized amount of data requested. And once that data comes back, then the SGL presented to the HBA is filled with the data, which is moved out of the data IU as they come in, the data IUs as they come in. And one important thing is,
it looks like somebody's actually anticipated your next slide and asked this question. I think it is a great time to set you up for this because it's a softball you can have apart. So FCE doesn't support RDMA. So does this mean that InfiniBand is a better transport than Fibre Channel? Take it away.
And actually, that's a good leading question, because really what RDMA allows you to enforce is zero copy. Basically, that means that you're not doing extra data copies to move things around in memory to get them ready to send or receive. RDMA is a semantic, which encourages the use of zero copy, but you don't need RDMA to do zero copy. FCP has been doing zero copy for over 20 years, probably close to 25 years without RDMA. RDMA is a set of APIs that make it easier to build deployments that do this efficiently, but it's not required to have those APIs to do it. So what I'm saying is that Fibre Channel also does zero copy with the FCP protocol. And I hope that answered the question.
I think it did. I guess we'll get more questions if it didn't, but I think it did.
Yep. And then another thing to look at is the transactions in the wire. If you look at the ladder diagram on the bottom, those are the transactions that take place for FCP data, and the next slide contains the data transactions for RDMA. And if you look at them, even though names have changed, the transactions are the same. So when it comes down to it, even if you have RDMA and you have remote memory access, you still have to move the data across a bit by bit across a network link, and the protocol or the transactions for doing that for both protocols are similar. Okay. On to discovery. So for Fibre Channel, there are two main types of topologies. There's the point-to-point topology, which means it's basically two devices connected together without a switch or a fabric. There is no name server in this configuration. There's no zoning. There are other fabric sensors don't exist. And this is used for smaller configurations that really don't need a large fabric. And of course, the more common topology is fabric-based, which consists of one or more Fibre Channel switches. Discovery is based around the Fibre Channel name server. Zoning is in effect, and these can be very large configurations, up to tens of thousands of ports. So for point-to-point, and I mention this because it is part of FC-NVMe, and it is mentioned in standard, but the discovery is basically either usually self-discovered or statically configured, and may use the NVMe discovery controller. Since there's no name server, there's no central point authority. Now, of course, for fabrics, discovery is based in Fibre Channel, based around the name server. So for FC-NVMe, we used a two-prong approach. We used the name server to identify the Fibre Channel ports, and we used the discovery service to identify the characteristics of the subsystems for NVMe. And this allows each component to store the data for which it has the authority on. So for example, if I have an FC-NVMe initiator and I want to go find some storage, I go first, this is similar to any other protocol like SCSI. I go first, ask the name server. And the name server will then point me to the discovery controller, which has information about the subsystems. So the initiator can then go talk to the discovery controller, and from there it can identify the subsystems that are associated with that port. And then at that point it can go talk to that and create connections to that subsystem. And then, of course, also FC-NVMe also works with the existing zoning and management server and other services that exist in Fibre Channel.
So we did get a couple questions that came in during your section, Craig. I hope you don't mind if I kind of interject
Go ahead.
and try to cover them now. I'll work in reverse chronological order, but since you just talked about zoning. Question came in: how does the zoning part? How will the zoning part be implemented on the switch side? Is it going to be using specific NVMe namespaces, or is it going to be done something internally into the name server?
Well, zoning is based on Fibre Channel characteristics, and even though these are at the end NVMe ports, for FC-NVMe they have all the standard Fibre Channel characteristics. They have a worldwide name. They have a Fibre Channel address, and so you would zone on any of those particular characteristics, either the worldwide name or the address, just like you do at SCSI. So the view for the administrator would be the same as it is for any other storage protocol. I could see that there may be additional add-ons that have additional information saying that these are NVMe ports, but the basic view and the basic configuration would be based on the Fibre Channel characteristics.
Okay, so there's no need for anything to be changed, in other words.
No.
Right. All right. So moving. All right. So moving back a little further, there's a question about the SGLs. In particular, is there a specific requirement for SGLs descriptor types that can be used with FC-NVMe?
There certainly are, and there's a certain type that is used for the Fibre Channel, and it's a transport specific or transport specific type that's defined in the NVMe specs that Fibre Channel then uses. And what I was presenting today wasn't going on that deeper level. If you look at the FC-NVMe specification, you can find out what that type, and we could also follow up with what the type value is in our follow-up session if people want to see that.
Yeah, it looks like it's going to be a good answer for the Q&A blog. And the last question before we move on into some implementation details: does the protocol support NVMe multi-queue?
Oh, it certainly does. Yeah, the protocol supports basically FC-NVMe protocol itself is a conduit for NVMe fabrics. So anything that the NVMe fabrics data feature set has is supported in FC-NVMe. So no matter how many protocol sort of queues or queue sets you have, that's supported.
Excellent. So we've gotten some more questions that are come in. I hope we can get to them, but I also know that we do have a lot more to cover. And I want to try to transfer this over to Curt so that he can get through his very important implementation details. And of course, if we can't get to all the questions, we will definitely answer them at the Q&A blog after the webinar is over. So I'm going to stop my question and blathering and turn it over to Curt to blather.
All right. Thank you, Jay. Thank you for the invitation to blather. I did just check on our time budget, and we're actually a couple of minutes ahead of schedule. And so I'm going to take this opportunity to say a little bit more because it really plays into this slide that I have here about the implications of how FC-NVMe has been implemented. So referencing at a higher level some of the questions that were asked earlier about, what about zoning, what about RDMA, what about queuing, what about SGLs? In the implementation of NVMe over Fibre Channel, or essentially creating the FC-NVMe specification, the decision, we could have said, the Fibre Channel community could have said, well, gee, we better go back and create RDMA. RDMA was developed with InfiniBand, which actually came after Fibre Channel. And so, as Craig mentioned, Fibre Channel was created to do zero copy. InfiniBand was aimed really at server clustering. I know this isn't a comparison of the different protocols, but anyway, they added RDMA for a more general purpose beyond storage. And then they decided to sort of popularize that on IP, and you really need RDMA to enable zero copy over an IP network. But then as the Fibre Channel community looked to implement NVMe, what we really wanted is what this slide is about, is to be able to run both SCSI and NVMe across the same infrastructure. And so they looked at, well, should we do RDMA? And the answer was, well, that'd be a heck of a lot of work, and it would actually make running concurrent protocols more difficult. So it would take a long time, add a lot of circuitry, and make things more difficult. So the goal was, from the beginning, to run these the SCSI and NVMe protocols on the same Fibre Channel infrastructure. And that means on the same HBAs, and I should say concurrently. Let me reiterate that. So that they can coexist concurrently on the same infrastructure. They run on the same HBA, the same driver, the same switches, the same Fibre Channel switches, and across the same links and so on. So typically the targets will have ports that will run either SCSI over Fibre Channel or NVMe over Fibre Channel, that is FC-SCSI or FC-NVMe. But the standard actually allows for a port to support both, and the fabric-based services will register that when devices log into the Fibre Channel SAN, and so other devices can look into the name server and decide or determine whether which protocols are supported by which devices that are connected. So basically, all that was a long setup to talk about this slide here, which is to say that the goal was to avoid rip and replace. We want to be able to provide, because we understand that storage is about protecting high-value data assets, and half of our job is to avoid risk or to manage risk. This was a model to minimize risk and to allow existing infrastructure to just incrementally migrate to an NVMe kind of a model, NVMe over Fibre Channel from a SCSI over Fibre Channel kind of situation on demand as the storage admin sees fit. And so they can do this on a volume by volume basis. Classically in SCSI, we map volumes to LUNs, SCSI LUNs. Someone mentioned in a question earlier namespace or namespace ID. Namespace ID is the mapping of effectively the equivalent of a SCSI LUN. So you would map a volume onto a SCSI LUN or a volume onto a NVMe namespace ID. In terms of in practical terms, both 16 gig and Gen 6 fabrics from both mainstream vendors will support NVMe over Fibre Channel, that is FC-NVMe, concurrently with FC-SCSI. Typically, the HBA vendors need the newer silicon. There's a tremendous amount of testing that goes in. And so it made more sense to support it on a HBA by HBA basis to require a move to the what they typically call Gen 6 silicon, although often it's offered in a Gen 5 speed, or I should say a 16 gig speed model. And it, how that's discussed will vary by the different vendors. In any case, once you've got an NVMe capable SAN, which you may already have, and an NVMe capable infrastructure, then you can run both FC-SCSI and FC-NVMe on that same infrastructure at the same time. You can have applications that have some volumes that are mapped onto SCSI LUNs and other volumes that are mapped onto FC-NVMe LUNs, or I should say NVMe namespace IDs. And as I said, this was the intent from the beginning when the Fibre Channel community began to implement NVMe on Fibre Channel to define the FC-NVMe specification. This has some additional ramifications, which I'll get to in these use cases. So based on our conversations, you may say, well, what's the difference? I mean, if it looks and smells a lot like the classic SCSI, except it runs faster, then what would be the different use cases? And that's a very good point. Actually, it is essentially, we expect to see the same use cases for FC-NVMe as we do on FC-SCSI. The earliest use cases will be latency-sensitive storage apps, most likely. That seems to be the biggest sensitivity initially is focusing on the lower latency of NVMe. And in addition, FC-NVMe. Most of that benefit shows up on the server side stack. There's a number of reasons for that. The FC fabric forwards the frames with the same latency, whether they're NVMe frames or whether they're SCSI frames. And then there's some variation on the target side. Classic SCSI storage arrays probably have a lot of enterprise features as sort of indicated in this picture, and there's some latency associated with the way those features have been implemented in the past. And so reduced latency comes to some degree from the target side and to some degree from the server side I/O stack. In addition, we'll see IOPS-sensitive storage apps. So one of the benefits of NVMe, we mentioned queues, and there was a question about multiple queues. Both the basic NVMe specification as well as NVMe over Fabrics, of which NVMe over Fibre Channel is an example of NVMe over Fabrics. They all support enhanced queuing. This is one reason why the NVMe protocol stack is more efficient than the SCSI protocol stack, because queuing was integrated into the protocol itself rather than being layered on top as it was with SCSI. By being layered on top with SCSI, there were additional context switching required on the server side, and that added a lot of wasted CPU clock cycles. So you get a kind of a double win with the enhanced queuing capabilities of the NVMe protocol. You get tremendous parallelism that comes from the extensive queuing capability that supports up to 64K queues and 64K entries per queue, as well as that much more efficient I/O stack. So you get reduced latency, but also a tremendous increase in the IOPS capability. That's very relevant today because we have so many VMs and cores and threads in our servers, and as well as a large number of servers as well. And now that we're moving from hard disk spinning media into solid state devices, the number of solid state devices in a storage array is a much larger number, and indeed each one of those individual solid state devices can actually support more parallelism than a classic hard disk can. So we have this large increase in parallelisms on both sides of the connection, and now with the enhanced queuing of the NVMe protocol, that can be taken advantage of. So those are two sort of classic applications that are supported in NVMe and just may do a better job of supporting our classic application. But we may also see new applications, what you might think of as memory applications. What I mean by that is typically storage has those enterprise features. Memory doesn't typically provide things like snapshot and recovery and various things. So if you have an application that's a little bit error tolerant, more than say enterprise storage, but really needs lower latency, this is where NVMe comes into play. And so we may see some applications. Typically those applications today are being done using a direct PCI connected environment, but there'll be a number of use cases like composable systems and so on, where they may prefer to have a shared resource and carve up the memory in that way, even if it comes at a slight increase in latency versus in comparison to a PCI attached device. So that'll be a new kind of application that we're likely to see in an FC-NVMe environment. And then there are also potentially combined applications. And this is actually quite powerful. This is something that it goes beyond the classic FC-SCSI model. And what it is essentially is use cases that take advantage of the dual protocol nature of basically the latest fiber channel SANs. The idea here is that you have a traditional database application running on a SCSI array, an FC-SCSI array that has all the enterprise storage features and supports a very high quality SLA to maintain a master copy of a database, for example, that is essentially a very important data asset. Now, you can do is use the features in that SCSI array to take a snapshot of that database, and that snapshot can then be migrated over to an NVMe subsystem with potentially a less intense SLA, but with a much lower latency. And then another application can use that copy, that reference copy of the database to do, say, data mining, or it might do machine learning or something like that, in which low latency is very important, but it can now leverage a copy of a database that is maintained in a master copy in the SCSI array. By having those on the same infrastructure, the ability to snapshot and clone copies is really very straightforward, whereas if they were in different infrastructures, it would be much more complicated and harder to, say, automate and run on a regular basis. So, as I say, familiar use cases, but potentially more latency or more parallelism is required, lower latency or more parallelism is required, and then there's new use cases as well. And with that, I will pass it back to Jay as he wraps up the presentation part of this, and I may talk to you again in a moment during Q&A.
That's right, because we do have quite a few queues for the A's. In fact, I think that probably working again in reverse chronological order while it's fresh in people's minds is the best policy. So the question came up, just a quick definition of terms. Is an NVMe subsystem an equivalent of a storage array? And considering you were just talking about those use cases, do you want to take that, Curt?
Sure. There can actually be more than one. I mean, the protocol and the standard allows for there to be more than one subsystem within an array. But I think often the implementations will be such that a storage array will be based on a single NVMe subsystem. So it's not, in a purely technical sense, it's not an exact mapping, but in a practical sense, it may often be, that may be a correct mapping.
Excellent. And as we go through some of these questions and comments, now is the time to go ahead and submit your questions, because this is the Q&A portion of the day. And so, Craig, I think this probably will go to you. Generally speaking, do you? I just lost it. Okay. The questioner is wondering if anyone knows where in the NVMe standard is support for asymmetric namespace support. Do you happen to have an insight about that?
No, I don't have an answer for that. I think that's something that's directed to the NVMe group.
Okay. Well, I want to make sure that everybody has the opportunity to answer it. The NVMe group has been working on this for several months now, and as soon as it will be finished, it will be released to the NVMe community. But currently, it's under development. Okay, so we have lots more. We weren't going to be doing a comparison of different types of NVMe fabrics transports, but I think that this goes to what Curt was talking about in terms of different kinds of use cases. So without trying to just skirting the entrance to the rabbit hole, Curt, can you give us some insights into the scenarios where NVMe using RDMA might be used in comparison or as opposed to NVMe-SC for accessing flash storage?
So essentially, they're very parallel notions. As Craig had sort of mentioned earlier, RDMA is a way to achieve zero copy when you're running on an IP Ethernet network, and that essentially is what the goal is there. If you are going to run on an IP Ethernet network, then the the faster implementation, the lowest latency implementations are probably going to be based on an RDMA, one of the RDMA options. There's a couple of choices out there. More recently, though, there's also been, and like you say, we're kind of circling the rabbit hole a little bit, but there's been NVMe TCP, which is sort of a similar notion, runs over an Ethernet IP network, but without RDMA. And that, just like Fibre Channel, it kind of highlights the fact that RDMA is not somehow coupled to NVMe. NVMe on PCI does not use RDMA. RDMA makes sense kind of in that InfiniBand or server clustering model where different servers are pushing data back and forth and they sort of take ownership of each other's, little sections of each other's memory. Storage is a different use case. It obviously, some people have figured that they could implement storage across RDMA, but it's not somehow specialized for storage at all. So I don't know if I've exactly answered the question, but if you wanted the lowest latency across an IP network, then you'd probably choose one of the RDMA implementations. If you run across Fibre Channel, then as we mentioned earlier, the choice was made to implement it without RDMA in order to provide a better incremental transitional implementation model. I would say you can't use the reason the NVMe over TCP protocol has been recently introduced as another fabric option is because existing infrastructure can't support RDMA. So existing NICs, for example, cannot support RDMA efficiently. So if you want to use existing infrastructure, then you should use NVMe over TCP, and that's why it was introduced, because of these large hyperscale data centers that do not want to replace every NIC.
That's excellent, and we've got a lot of stuff coming in, so I can already tell we're not going to be able to answer all of them, but these are fantastic questions. We wanted an advanced deep dive, and these are advanced deep dive questions. So, Craig, I've got one for you. This questioner says some basic questions. How are multiple queues supported in the NVMe over Fabrics environment? Does the HPA vendor need to implement these submission queue and completion queue supports inside of the drivers, as well with target vendors have to implement these from their side?
Okay, so definitely, it impacts, I think, the target more than it does the HPA, because really the queues are directed toward the storage subsystem controller. I can't say how any specific implementation is going to work, but you definitely would have to have the resources in the target to handle the queues. Now, on the initiator or the host, basically the resources required there are to keep track of how full the queues are and what the positions of the queue pointers are, so that you don't overflow the queue. And so in a typical implementation on the initiator side or host side, the resources would likely be a lot smaller for maintaining both queues.
Right. Well, we have a couple more minutes for a couple more questions. And so this one's going to go to you, Craig. I think that this is probably right up your alley. I'm going to combine two of the questions that come in. So one of the questions is, can you explain where the lower latency comes from using NVMe? And what kind of latency should we expect with NVMe over Fibre Channel with 32 gig in particular, without the drive latency itself?
Okay, so I'll take the second question first, because that really answers this first question. We're not speeding up the fabric by putting NVMe over it. The fabric latency is going to be the fabric latency no matter what protocol you're running. That's the same as you see in or TCP, RDMA. The latency is built into what the fabric can do, and it all has to do with the equipment you're using. It has to do with the lengths of how long the links you have between elements are. If you start getting longer lengths, then you can start introducing latency that way. So there's a lot of factors that go into that. Really, the latency improvements come in at both ends, where you have a lighter weight protocol on both ends, and you have a high-speed NVM non-volatile memory device on the target side. And that's really where the latency comes in. And you know, I can't say what the a typical latency is because a typical latency is going to depend on the fabric topology.
Excellent. Unfortunately, even though we've got some fantastic questions that I really wanted to be able to get to, we just don't have the time. So I will say that we will get to those questions and any others that come in the last few minutes. By all means, please feel free to submit questions. We will respond to them in written format on our Q&A blog as soon as we possibly can. For now, though, let's go ahead and try to summarize what we've seen so far and give you a little bit of information as to what to expect next. I want to thank both Curt and Craig for taking the time out of their busy days to break this down for everybody. There are a lot of technical details in this webinar, and if you're one of those people who can remember minute details after seeing it only once, you're amazing. For mere mortals like myself, though, let me summarize a bit about what we talked about at a higher level. First, FC-NVMe is wicked fast, as we used to say in Rhode Island. It's wicked fast and built upon 20 years of storage networking experience. It's also highly flexible and can be run side by side with existing SCSI-based environments, inherits all of the benefits from having a true discovery and named service fabric. Perhaps most important for some people, it's built upon the trusted end-to-end qualification and interoperability matrices that are required for some storage deployments. And that kind of level of comfort is extremely important. We have some milestones, and one of the questions that comes up often is when. So the good news is that the FC-NVMe standard just completed the first round of approval at the T11.3 committee. And what this means is that it's technically stable and that vendors can feel assured that the specifics aren't going to change and that products can be developed to that specification. Now, after this webcast, now that we're wrapping it up, before you go, let me give you some more information about where to get more information. First, please rate this event. I cannot stress enough how much we value your input. These webinars take quite a bit of work, and we want to make sure that we're working hard and smart to make something valuable for you. Second, we're going to be taking all of the questions and creating a Q&A blog post, and we'll be putting it on the fibrechannel.org website very soon. Also, to that point, the PDF for these slides will be posted shortly, as soon as next week, at the fibrechannel.org website as well. Of course, we would like to invite you to our next webinar about Fibre Channel and distance solutions. There are a lot of questions that often come up about disaster recovery, business continuity, and storage access across distances, and, of course, what's going to happen with the new NVMe stuff. So we'll be taking a look at how fast the propeller spins the other way on October 10th. So you can find out more about that announcement and more of what we're doing if you're curious about the nature of Fibre Channel by following us on Twitter at FCIA News. So, again, thank you so much for taking time out of your day. A huge thank you to both Craig and Curt, who I can tell you from personal experience have been spending a lot of time to make this enjoyable for you. So, again, please submit any additional last-minute questions. Please rate, offer comments, and join us again in our next webinar. Thank you so much.